dark matter. It's the most mysterious substance in the universe. Little is known about it. Scientists are pretty sure it exists, but still don't know what it is. Now they have created the largest ever distribution map of dark matter in the universe.
Have you ever looked up at the night sky and wondered what mysteries it holds? Scientists and astronomers have been on a mission to uncover the secrets of our cosmos for decades, and one of their greatest curiosities is dark matter. Despite years of research, the enigma that is dark matter has remained unsolved, until now. A team of scientists researching dark matter have made an incredible discovery, a portal leading to the fifth dimension. This breakthrough has the potential to revolutionize our understanding of the universe. But how did they make this discovery? And what does it mean for us? Join us as we embark on a journey to explore this mind-bending revelation that could change the way we perceive the universe. Imagine yourself standing in an empty room with a cube in front of you. You kick it across the floor with all your might, watching it as it moves through space. In those few seconds of its motion, you're witnessing the interplay of 4 dimensions: height, width, depth, and time. The first 3 dimensions are visible on the cube itself, but time is the dimension you see in its progression. While we can't actually see time itself, its progression through space is as close as we can get to visualizing it. But did you know that there's a 5th dimension? Unlike the first 4 dimensions, the 5th dimension is considered to be a micro-dimension, one that we can't perceive in our daily lives. Physicists introduced the 5th dimension in an attempt to connect all parts of the universe and make sense of fundamental forces such as gravity and electromagnetic force. This 5th dimension has the potential to revolutionize the way we view the universe and our place in it. This became known as the Kaluza-Klein theory, which has the ultimate goal of connecting gravity and electromagnetic force into a 5th dimension. However, before we delve into the fascinating Kaluza-Klein theory, let's first explore the intriguing discovery made by scientists about the 5th dimension. For a long time, dark matter has remained a puzzle that scientists and astronomers are still trying to solve. Despite taking up most of our universe, dark matter remains largely a mystery. However, with the revelation of the 5th dimension, scientists believe that this new dimension could be the missing piece in explaining the 75% of dark matter that has yet to be observed. Although we don't know much about dark matter, it's essential in our understanding of the universe. Dark matter is crucial because it takes up most of our universe and helps scientists explain how gravity works. Scientists believe that without dark matter, many features of our universe would fall apart. Despite its significance, dark matter does not seem to have a direct effect on the particles we see and feel, suggesting that it has other unique properties that we're yet to discover. This is why scientists are continuously researching dark matter to unravel its mysteries. Recently, a group of physicists from Johannes Gutenberg University in Mainz, Germany, conducted a study in order to gain a deeper understanding of dark matter and its properties. The study proposed a theory that there are unknown particles that move around in a 5th dimension that is hidden from our 4-dimensional universe. These particles could be responsible for the extra gravity that we currently attribute to dark matter. The study was published in the European physical journal C, and it suggests that this particle can offer a concrete explanation for dark matter, which is believed to make up the majority of the universe's total mass. While this phenomenon has never been directly studied, the findings of this study offer an intriguing avenue for further exploration of the mysterious properties of dark matter. The researchers explain in their study that particles could travel across the entire universe, including the newly discovered 5th dimension. Scientists have been debating the 4 dimensions of our universe for decades, which are 3 dimensions of space, up and down, left and right, and back and forth, and 1 dimension of time. Scientists have developed 5D equations based on extensive research that suggest the implications of the extra dimension on the universe and even reality itself. The study's authors, Adrian Carmona, Javier Castellano Ruiz, and Matthias Neubert, stated that discovering the 5th dimension was not their original goal. Their initial goal was to explain the likely origins of fermion particles in warped extra-dimensional theories. they discovered a new scalar while researching 5D equations and how they relate to fermion particle masses. A scalar is a physical quantity defined primarily by its magnitude. They claim that this newly sketched out scalar is very similar to the Higgs boson particle and the Higgs field. The scientists discovered that the new scalar field exhibited unusual and intriguing behavior along the extra dimension. After making this discovery, they stated in a statement, "We believe the existence of these heavy particles would join the visible matter that we know and that we have studied in detail, the constituents of dark matter. We believe this based on the assumption that dark matter is composed of fundamental fermions which live in the extra dimension." The authors of the study discussed a heavy particle that they believe could serve as a new messenger to the dark sector. Their theory explains the abundance of dark matter in the universe as observed by astrophysical experiments and provides new, more exciting methods to uncover the constituents of dark matter. These methods would involve taking a detour through the extra dimension to gather information about the physics of the dimension during the early stages of the universe when dark matter was produced. The study's lead researcher, Matthias Neubert, expressed his confidence in the theory, noting that years of possible confirmations of the team's theoretical predictions have led them to this point. He continued further, "We are confident because the mechanism discovered would make dark matter accessible to forthcoming experiments due to properties of the new interaction between ordinary matter and dark matter. It would be mediated by our proposed particle and can be calculated accurately within our theory. Therefore, we hope the new particle may be discovered first through its interactions with the dark sector." Although creating a hypothesis about the particle and its masses is only the beginning, or to put it another way, the easy part, these scientists would now have to search for it. The Nobel Prize-winning discovery of the Higgs boson is one example. The Large Hadron Collider, the world's largest and most powerful particle accelerator, discovered the Higgs boson. The Higgs boson was discovered in 2012, but its hypothesis was first proposed in 1964. Unfortunately, because this new particle is too heavy for current colliders, the Large Hadron Collider would not be large or powerful enough to detect it. Regardless, the scientists who proposed this study are crossing their fingers that the particle can be detected indirectly. They believe that this new particle could have a significant impact on the cosmological history of our universe. They also believe it may generate gravitational waves that can be detected using gravitational wave detectors. So, what is the mathematical stance of the fifth dimension? Remember that we talked about the Kaluza-Klein theory? It's an interesting bit of physics history that, while not actively researched today, was the first example of a unification theory by adding an extra dimension and is considered by many to be the precursor of string theory. The origins can be traced back to shortly after the publication of general relativity. While looking at the Einstein equations in 5 dimensions rather than 4, Theodore Kaluza noticed that imposing something called the cylinder condition on it made the equations noticeably simpler. This is the same as saying that the fifth dimension is a closed loop rather than an infinitely long straight line. Using this assumption, he derived the equations of motion along the 5D paths and discovered that, in the absence of forces, they became roughly the same as those in GR that were subject to electromagnetic forces. This result sparked interest in the unification of nature's fundamental forces through the addition of extra dimensions, particularly those with cylinder conditions of small radius. The majority of the remaining theories were quantum in nature. Oscar Klein was interested in how this might translate to quantum mechanics in the classical versions of this theory. The results were intriguing and provided a significant stepping stone to similar unification theories, but some predictions were incorrect. While this theory is no longer actively considered a candidate for our current laws of physics, it is still an important piece of physics history, and understanding it can help provide a gateway to understanding the theories that have branched from it. In later years, it was discovered that some of the calculations included in the theory were slightly off, but these calculations did provide a basis for a later mathematical claim that surrounds the fifth microdimension. The initial calculations, which were performed using the Kaluza-Klein theory, involved rolling the fifth dimension into a dense loop that would have been approximately 10 to the negative 33 centimeters in size. From this point, Oscar Klein reasoned that light was something that occurred more in the fifth dimension, and that what we saw of it was a more watered-down version of what really existed. Think of it like when you swim underwater in a pool and there are ripples on the still surface. You'd see the ripples as shadows rather than the ripples they were. This was how Klein conceived of light, with the vast majority of it taking place in the fifth dimension. It was through this method that he was able to establish a connection between the two primary forces of gravity and electromagnetism, which in our observable universe only appear to be indirectly related to one another. After some time, the whole concept eventually morphed into the idea of superstring theory and supergravity, which eventually developed into M-theory. Ultimately, the Kaluza-Klein theory has become more of a gauge theory, meaning it fits into a certain type of field theory in which the Lagrangian doesn't change under local transformations. When we look at what evidence there is for a fifth dimension, there isn't much. Because we've already established that it's a dimension that isn't perceivable to us, the fifth dimension would be extremely challenging to observe under any circumstances. Just like swimming underwater, you don't see the ripples. The same principles apply here. You won't be able to view the fifth dimension because it exists on a different plane and is above you. However, this does not necessarily imply that all hope is lost. Rather, it is time to examine the evidence that has already been gathered, primarily by the Large Hadron Collider, one of the world's largest particle colliders. The most important thing to remember here is that we're still speculating on a fifth dimension. While it is widely accepted in the physics and mathematical communities due to the amount of sense it makes when discussing equations, we still can't observe and fully confirm its existence. However, with the assistance of the Large Hadron Collider, there has been more evidence of its importance in the universe. There is the hypothesis presented here that the collision of subatomic particles results in the production of additional particles, one of which could be theoretical graviton. In this scenario, the graviton leaves the fourth dimension and leaks into the fifth dimension bulk. Through this, there's more of an explanation which comes from why gravity is so weak. Although we consider gravity to be relatively strong, it is considered weak due to how easily it can be overcome in certain circumstances, particularly by other forces. Consider making an electromagnet. You can lift objects using an electromagnet. This eventually pulls them away from gravity, making the electromagnet a stronger force. Having gravity be a weaker force makes slightly more sense in a five-dimensional space, which is why it's widely considered to be a theoretical construct, especially when discussing physics. Not only that, but it's said to be a micro-dimension because it doesn't have full access to us. We can't see it even though we interact with it. Visualize it in terms of the colonists in early America, and the difference between their situation and that of the British. In this particular example, colonial America stands in for the four dimensions that are being interacted with. However, England, or Great Britain, did not really have the same nature of being present in colonial America, and despite the fact that they interacted with it somewhat, it was not there for the majority of the time. Lastly, it makes way for other theories that do need more than one dimension, and that need this seamless tie between the fundamental forces. Later on, the Einstein-Maxwell theory worked with the fifth dimension, trying to get it so that it would be derived from a distance. Initially, the idea had been to try and fit electromagnetism into its own slot in what we know as space-time, but that didn't quite work. Up to this point, the suggestion and usage of the fifth dimension is the best we're going to get. Now, let's return to dark matter and a recent discovery about it. Recently, astronomers using the Hubble Space Telescope have stumbled upon an unexpected phenomenon. When they observed 11 galaxy clusters, they noticed something strange. The cluster's galaxies were giving off 10 times more gravitational lensing effects than expected. This discovery led scientists to review the current dark matter theories and conclude that the dark matter halos may be even bigger and denser than we previously thought, according to the standard cosmological model. In 1933, a Swiss astronomer named Fritz Zwicky, who was working at the California Institute of Technology, was studying the Coma Galaxy cluster when he noticed something odd. According to the measure of visible mass, the individual galaxies were moving too fast for the cluster to remain whole. Only a specific amount of invisible matter could account for the powerful gravitational force that holds the galaxies together. Following that incident, scientists investigated the occurrence and labeled the matter dark due to its inability to emit or absorb any form of light. Its presence could only be detected or revealed through gravitational interaction with ordinary matter. More research on this so-called dark matter has been conducted since then. Observations from various studies suggest that this unusual phenomenon is a significant part of the universe's matter, accounting for approximately 75% of the universe's matter. In the standard cosmological model, it is referred to as cold dark matter, CDM. Cold dark matter is thought to be made up of massively interacting particles, but they are weak and their physical nature is unknown. Dark matter halos that are gravitationally bound would form a hierarchical structure in this CDM perspective. These dark matter halos would form from the most massive systems merging with smaller ones. Large dark matter halos would contain smaller substructures in the form of embedded subhalos as the dark matter halos form together in this hierarchical structure. Galaxy clusters are similar in this regard. They too have large dark matter halos containing hundreds of galaxies gathered in subhalos. The evolution of these galaxy clusters with the interaction of luminous and dark matter is carefully observed and theoretically studied using cosmological simulations. These observations and comparisons allow scientists to put the standard cosmological model to the test. Galaxy clusters are the most important structures that hold our universe together. Their combined mass may exceed a quadrillion solar masses. When viewed through the lens of Einstein's general theory of relativity, their enormous mass diverts the light of distant galaxies, sometimes deforming and splitting them into multiple images. Gravitational lensing is the process of observing this phenomenon. Scientists can use gravitational lensing to determine the spatial distribution of both ordinary and dark matter in cluster cores, where density mass is extremely high. The principle of gravitational lensing is not difficult to understand. All scientists need to do is reverse engineer the observed image distortions to determine the mass distributions of the lens. Tens of imaged galaxies were lensed by 11 massive galaxy clusters recently observed with the Hubble Space Telescope. The observation was done in the framework of two programs, cluster lensing and supernova survey with Hubble and Hubble Frontier Fields. Astronomers used the multi-unit spectroscopic explorer mounted on Chile's Very Large Telescope to improve their ability to compile the total distribution on the smallest scales. They used the telescope to measure the velocity dissipation of stars in 3 clusters of galaxies: MAX J1206 plus 0847, MAX J0416.1-2403, and Able S1063 are the names of these clusters. Because stars are powered by the effects of gravity, their momentum serves as a deputy for the masses of any subhalos that they orbit. By combining gravitational lensing with the galaxy kinematics measurements obtained from MUSE, which is a powerful wide-field and optical integral field spectrograph, the group of researchers was able to obtain high-resolution mass maps of each galaxy cluster. These maps also demonstrate that the cluster galaxies in question are surrounded by enormous, dense subhalos of dark matter. Images of distant sources magnified by foreground galaxy clusters are separated by tens of arcseconds. As a result, subhalos within each cluster function as smaller-scale gravitational lenses embedded within larger lenses. If these subhalos are large enough and dense enough, they may produce additional local strong lensing events on smaller scales with separations of less than a few arcseconds. These events, known as galaxy-galaxy strong lensing (GGSL) events, were caused by scientists lensing mass reconstructions in each of the observed clusters. Scientists then compared the observed cluster mass distributions to 25 simulated galaxy clusters that evolved in the standard cosmological model. This comparison revealed that on the smallest scales, cosmological simulations do not depict the same dark matter concentration level. This is why they produce more than 10 times the number of galaxy-galaxy strong lensing events we're able to observe. These findings suggest that there are some aspects of the universe that we do not yet understand. As a result, the observed number of GGSL events contradicts theoretical predictions about the standard cosmological model. It could also be a problem with the simulation methods, Or we could have made incorrect assumptions about the properties of dark matter. More observations, however, will be made using equipment such as the European Space Agency's telescope and NASA's planned Euclid. By increasing the number of cluster samples that can be examined, the Nancy Grace Roman Space Telescope could help confirm the problem and clarify issues. This would aid scientists and astronomers in their efforts to stress test dark matter models. Furthermore, for many years, scientists have been puzzled about where dark energy comes from. They came up with the idea of dark energy to explain why the universe is expanding at an accelerating rate, even though gravity should be slowing things down. However, the origin of this force has remained a mystery. A team of 17 researchers led by the University of Hawaii may have finally found the answer. They have discovered evidence that suggests black holes could be the origin point of dark energy. Black holes grow in two ways: by merging with other black holes or by accreting gas. However, after studying the evolution of black holes in giant elliptical galaxies for 9 billion years, the researchers found that older black holes were much larger than expected based on these two growth methods. This suggests that there is another way for black holes to acquire mass, and the researchers believe it could be through dark energy in the form of vacuum energy, which is a type of energy that exists within space-time and accelerates the universe's expansion. If their theory is correct, it would be a groundbreaking discovery that could revolutionize cosmology. For over 20 years, cosmologists and theoretical physicists have been trying to solve the mystery of dark energy, and the discovery that black holes could be its source could provide the answer. While the idea of black holes being a source of dark energy has been part of Einstein's theory of general relativity, this is the first time observational evidence has been found to support it. Now, let's hear your thoughts about these findings in the comments section below.